Mars looks silent from the surface. Around NASA's InSight lander, the ground stretches outward in a cold plain of dust, scattered stones, and muted red light. Nothing in that scene suggests an enormous discovery. There is no open cavern, no exposed underground sea, and no machine drilling through the crust. The lander itself no longer moves or listens. Its mission ended in 2022, after dust slowly reduced the power reaching its solar panels. Yet the most important part of its work did not end when the spacecraft fell quiet. For years, InSight had been measuring movements so small that a person standing nearby would never have felt most of them. Its seismometer recorded more than 1,300 seismic events, vibrations produced by marsquakes, impacts, and stresses within the planet. Each event sent waves through layers of rock before those waves reached the instrument. The lander stored their arrival times, strengths, and changing patterns. Long after the final signal from the mission, scientists could continue studying that record. Hidden inside it was evidence that the planet beneath the dry plain might be very different from the planet visible above it. The contradiction begins at the boundary between what can be seen and what must be inferred. From orbit, Mars offers familiar evidence of absence: empty channels, exposed rock, and a thin atmosphere above a frozen desert. InSight offered something different. It did not observe the shape of a buried feature. It measured how the planet responded when energy passed through it. The discovery, therefore, exists not as a picture, but as a chain of reasoning connecting faint movements at the surface to possible conditions far below. When researchers compared the seismic measurements with gravity information and models of possible Martian rocks, one interpretation stood out. The middle part of the crust beneath InSight could consist of fractured rock whose narrow pores and cracks contain liquid water. This proposed zone lies many kilometers below the surface, beyond any place directly reached by a Mars mission. The possible amount is what made the result extraordinary. If similar conditions extend far beyond the landing site, the water stored within the crust could equal enough liquid to cover the entire planet in a layer between 1 and 2 kilometers deep. That comparison describes a total volume. It does not mean that scientists found a continuous ocean with a surface, shorelines, or empty space above it. The proposed water would be distributed through rock, and the planet-wide estimate depends on conditions beneath one location being common elsewhere. This distinction changes the meaning of the headline. NASA did not photograph something enormous beneath Mars. InSight did not lower a camera into a hidden chamber, and it did not drill into an aquifer. It recorded the motion of the ground. Scientists then used physics and statistical models to ask what kind of material could have produced the measured signals. Those signals provide evidence, but they do not label the substance through which they traveled. Seismic waves change speed when rock density, temperature, fractures, or pore contents change. More than one combination can sometimes produce a similar result. Liquid water may offer the strongest explanation within a particular model without becoming a direct observation. That uncertainty does not make the finding unimportant. It defines the real mystery. A world famous for its dry surface may still hold a major part of its ancient water deep inside its crust. A silent lander, listening from one small patch of ground, may have detected the trace of a reservoir vast enough to alter the story of an entire planet. But before those vibrations can be understood as water, there is an older question to answer. Mars once carried rivers across its surface and collected water in lakes. Today, those landscapes are empty. To understand what InSight may have found beneath the planet, we must first understand what Mars appears to have lost. The surface of Mars does not merely suggest that water once existed there. In many places, it preserves the paths that water followed. Broad channels cut across old terrain. Branching valleys resemble drainage systems. Fan-shaped deltas spread into ancient basins where rivers appear to have slowed and dropped the material they carried. Layered sediments remain inside craters that once held lakes. Minerals altered through contact with water are locked into rocks that have been dry for immense periods. The landscape serves as a record, although not a complete one. A valley can show that fluid moved downhill, but it cannot by itself reveal how long the flow lasted or how much water existed elsewhere. A delta can mark an ancient shoreline, while leaving its age and duration uncertain. Each feature provides a piece of the history, and the pieces must be joined carefully. These features were not created by one brief event. Together, they describe a planet that passed through several wet conditions across a long and complicated history. Water flowed over open ground, collected in low areas, entered the soil, froze, melted, evaporated, and reacted with rock. Some environments may have lasted far longer than others. Some may have been limited to particular regions or warmer periods. The exact climate remains debated, but the larger conclusion is difficult to avoid. Ancient Mars had far more moving surface water than modern Mars. That creates a striking contrast. Today, liquid water cannot remain stable for long across most of the Martian surface. The atmosphere is thin, the pressure is low, and the planet is cold. Exposed liquid would tend to freeze, evaporate, or pass directly into vapor under local conditions. The channels remain, but the rivers that shaped them are gone. The lake basins remain, but their open water has vanished. The change was tied to a transformation of the planet itself. Early Mars possessed a thicker atmosphere, creating pressure and temperatures that could sometimes support water at the surface. As the atmosphere thinned, those conditions became harder to maintain. Water exposed at the surface was no longer protected by the same environment. Across immense spans of time, part of the planet's water entered the atmosphere, and part of that atmospheric material escaped into space, permanently reducing the amount that remained on Mars. Atmospheric escape therefore supplies one destination for ancient water, but it cannot be treated as a complete and measured answer. Scientists must reconstruct a process that unfolded over billions of years from evidence still available today. The result establishes that water was lost from Mars, while leaving uncertainty about exactly how much of the original inventory followed that path. But atmospheric escape is not the whole answer. Water can disappear from view without leaving a planet. Some Martian water survives as ice. Large quantities are stored at the poles, and more ice exists beneath the ground in other regions. Frozen water can remain stable when it is protected from direct exposure. Over changing seasons and climate cycles, some of it can shift between the surface and atmosphere. Yet the ice detected today represents only one part of a much larger and older system. Another portion became part of the rocks themselves. Water reacts with minerals. During those reactions, hydrogen and oxygen can enter new chemical structures instead of remaining as free liquid or ice. The resulting hydrated minerals preserve evidence of past contact with water, but the water bound inside them is no longer flowing through rivers. It has become part of the solid planet. Water could also travel downward. Cracks, porous layers, impacts, volcanic heating, and changing pressure can move fluids through a crust. On Earth, enormous amounts of water exist beneath the surface without forming open underground seas. They occupy pores, fractures, and connected spaces within rock. Ancient Mars may also have transferred part of its surface water into its crust before the planet above became the desert seen today. These destinations create a planetary water ledger. One part escaped to space, one part froze, one part entered minerals. Another part may have moved deeper underground. The challenge is that scientists do not know the original total with perfect accuracy, and none of the surviving reservoirs has been mapped completely. Estimates of ancient oceans depend on the shorelines, sediments, climate models, and geological periods being considered. The amount lost through the atmosphere also has to be reconstructed from evidence collected long after most of the loss occurred. For that reason, the question is not simply whether Mars lost its water, it is how much followed each path. If most of the ancient inventory escaped into space, modern Mars is a planet from which a vital resource was physically removed. If much of it became ice or entered minerals, the water still exists, but in forms shaped by billions of years of change. If a large amount descended into the crust and remained liquid, then the dry surface has concealed a major chapter of the planet's history. That possibility would change how scientists reconstruct the water ledger of Mars. A deep reservoir could mean that material missing from the surface was not removed from the planet. Instead, it may have changed location, becoming hidden as the crust evolved above it. The surface transition from wet to dry would then describe what became visible, not necessarily the fate of every store of Martian water. None of this means that a deep liquid reservoir must be present. The ancient water budget is uncertain, and several destinations can operate at the same time. Mars did not need to lose its water through one dramatic event. The transformation could have unfolded slowly, with different portions escaping, freezing, reacting with minerals, or moving downward during different eras. This is why the evidence from beneath Elysium Planitia matters. It may connect a modern measurement with a mystery written across ancient landscapes. The empty channels show that water was once available at the surface. The thin atmosphere explains why much of it could not remain there. Ice and altered minerals account for some of what survived, but they leave room for another destination, hidden far below the reach of cameras and rovers. Testing that possibility required scientists to examine a region no drill had entered. They needed to measure the physical character of buried rock through kilometers of crust while working from a single position on the surface. The answer would depend not on seeing the hidden layers, but on listening to energy pass through them. For that task, NASA placed an unusually sensitive instrument on Mars and waited for the planet to move. NASA's InSight lander reached Mars in 2018 with a purpose different from that of a rover. It was not designed to travel from one rock formation to another. It would remain in one place and study movements that could not be seen. The mission depended on patience. Instead of crossing the surface to examine many locations, InSight would wait for distant events to send information toward it through the planet. Its most important instrument was a highly sensitive seismometer placed directly on the Martian ground. A seismometer measures motion. When the surface shifts, even by a tiny amount, the instrument records how that movement changes over time. The result is not a photograph of the source or of the layers below. It is a pattern showing when the ground moved, how strongly it moved, and how the motion developed. On Earth, networks of seismometers record earthquakes from many positions. Their combined measurements help scientists locate an event and follow different wave paths through the planet. InSight had to work under a much tighter limit. It was one listening station on an entire world. Every useful signal had to reach the same small area of Elysium Planitia. no matter where the event began. Mars nevertheless supplied natural sources of seismic energy. Stresses within the planet produced marsquakes. Meteoroids struck the surface and sent vibrations into the ground. Some events occurred nearby, while others began much farther from the lander. Their signals traveled through different depths and regions before arriving at the instrument. Each path offered a different sample of the hidden interior. The energy did not remain in one simple pulse. As vibrations encountered changes within Mars, parts of the signal could arrive at different times or with different strengths and patterns. Some paths stayed relatively shallow. Others passed through deeper material. InSight did not need to visit those places physically. The waves had already traveled through them, carrying the effects of what they encountered. The instrument recorded those effects as data. Scientists could examine when a signal began, how long it continued, which frequencies were present, and how its amplitude changed. They could compare the arrival of one part of an event with another. Patterns that appeared across several events could become more useful than any single recording, because repeated behavior could point toward a shared feature of the planet rather than an unusual source. Not every recorded movement provided the same amount of information. Some signals were faint, incomplete, or difficult to connect with a source. The task was therefore not simply to notice that the ground had moved. Researchers had to compare events, judge the confidence of each detection, and decide which parts of the archive could support an investigation of the interior. Impacts provided an especially useful connection between the surface and the seismic record. When orbital images identified a newly formed crater, scientists could link a visible location with vibrations detected by InSight. That connection supplied information about where an event occurred, reducing one source of uncertainty. The impact had acted as a natural experiment. An event at the surface sent energy through Mars to the waiting instrument. During the mission, InSight recorded more than 1,300 seismic events. They were not all equal. Some were stronger, clearer, or better located than others. Some sampled parts of the planet that other signals did not reach. Together, however, they formed the first long seismic record collected directly from the surface of Mars. Building this archive required consistency. A faint movement becomes scientifically useful only when researchers can place it within an organized record and compare it with other events. The date, duration, strength, and confidence of each detection help determine what questions it can address. A poorly located event may still reveal that Mars is active, while a clearer signal with supporting orbital evidence can carry stronger information about its route. The catalog therefore did more than count marsquakes. It created a body of measurements in which events could support, challenge, or clarify patterns seen in the rest. The value of that record extended beyond the operating life of the lander. InSight's power declined as dust reduced the sunlight reaching its solar panels, and the mission ended in 2022. But the measurements had already been stored and returned. Scientists could revisit them with new questions, compare them with revised models, or identify relationships that were not apparent during the first analysis. This is how a silent machine could continue producing discoveries. The lander was no longer gathering new movements, yet the old movements had not been fully interpreted. A signal can contain more information than researchers are able to extract immediately. When a better method or a new comparison becomes available, the same recording can support a different investigation. The distinction between measurement and interpretation is essential. InSight measured ground motion. It did not measure a container labeled water. It did not report that a particular layer was made from one type of rock. It did not create a complete picture of every point beneath Mars. Those conclusions had to be reconstructed by asking what internal conditions could produce the recorded behavior. Even the source of a signal could carry uncertainty. With a global network, several stations can compare arrival times and narrow down an event's location. With one station, researchers have fewer lines of sight. They must use the shape of the signal, other available observations, and assumptions about the planet to estimate where an event began and which route its energy followed. The interior introduces another difficulty. A wave can change because of the material it crosses, the temperature of that material, the presence of fractures, or the depth and angle of its path. If several unknowns affect the same recording, scientists must compare many possible explanations. A model that matches the measurements well becomes meaningful, but it does not turn the hidden interior into something directly observed. This limitation does not reduce insight to guesswork. The signals obey physical rules, and possible interiors cannot produce any pattern researchers choose. Arrival times, amplitudes, frequencies, and repeated relationships restrict which explanations remain plausible. Information from impacts, orbital observations, and other measurements can narrow those possibilities further. The result is a constrained investigation, even when it cannot deliver perfect certainty. Insight therefore changed the way Mars could be explored. Before the lander, the deep planet was largely beyond direct measurement. After it, every useful marsquake became a probe that Mars generated for itself. No drill had to reach the mantle. No camera had to enter the crust. Energy traveled through the hidden layers and returned their influence to one instrument on the surface. That influence was subtle, indirect, and incomplete, but it was real. More than 1,300 events gave researchers many chances to compare how Mars responded. Some recordings helped reveal broad boundaries. Others carried information about particular depths or regions. The possible water beneath Elysium Planitia emerged from this larger archive, not from a single dramatic signal announcing what it had crossed. The instrument had supplied the evidence baseline. Tiny movements, measured across years, from natural events scattered through and around another world. The next task was to translate those movements into physical structure. To do that, scientists had to understand why a wave moves quickly through one material, slowly through another, weakens along one path, and changes when the spaces inside rock contain something different. Only then could a vibration recorded at the surface begin to act like a map of what lay below. A seismic recording begins as movement, but the movement is not random. Every part of the signal has been shaped by a journey. The energy left its source, crossed material inside Mars, and eventually disturbed the ground beneath InSight. If scientists can understand how different materials affect that journey, they can work backward from the recorded pattern toward a set of possible interiors. The first useful clue is time. A wave does not move at the same speed through every substance. Its speed depends on how strongly the material resists being compressed or changed in shape, as well as on its density. More rigid material can pass certain vibrations differently from material that is fractured, warmer, softer, or partly filled with another substance. The arrival time therefore carries information about the physical conditions along the path. But arrival time alone is not enough. Scientists also examine the strength of the signal, the range of frequencies it contains, and the way different parts of the motion appear. Energy can weaken as it travels. It can be redirected, reflected, or spread by boundaries and irregular regions. A useful model must account for several features together rather than matching one number while ignoring the rest. Two broad kinds of seismic motion help constrain what lies below. P waves involve compression. Material is pushed and released in the direction the wave travels. S waves involve a change in shape, with movement across the direction of travel. Because these motions place different demands on the material, they do not respond to internal conditions in exactly the same way. Comparing them gives researchers more information than either would provide alone. The important point is not the names of the waves. It is that each type tests a different part of the material's behavior. A layer that allows compressional motion to pass at one speed while changing shear motion in another way cannot be represented by just any rock. The combination reduces the number of internal structures able to reproduce the observations. Rock itself is not a perfectly uniform solid. It can contain pores, narrow cracks, larger fractures, and boundaries between minerals. These spaces affect how firmly one part of the rock responds to another when seismic energy passes. A tightly connected block behaves differently from material crossed by many open fractures. Even when the solid minerals remain the same, the arrangement of empty space can alter the measured result. What occupies that space also matters. A pore might be relatively empty, filled with gas, occupied by ice, lined or filled by other minerals, or contain liquid. Each possibility changes the combined physical response of the rock. The effect depends on how much pore space exists, how well the spaces connect, and how fully a material occupies them. Scientists therefore cannot look at one wave speed and simply translate it into the word water. Density and rigidity must also be kept carefully separate in the reasoning. Two materials can have similar densities while responding differently when squeezed or bent. Conversely, two layers may pass a wave at comparable speeds even though their masses are distributed differently. This is one reason a single measurement rarely identifies a unique composition. Researchers need several properties that intersect at once. Each observation removes part of the range of possible interiors, like several overlapping filters that leave a smaller area in common. The remaining area may still contain multiple answers, but those answers must satisfy the same combined physical limits rather than merely resembling one selected feature of the signal. Instead, they build rock physics models. These models connect a proposed mixture of solid rock, fractures, and pore contents with properties that seismic waves and gravity can test. Knowledge of how igneous rock behaves supplies a starting point. Researchers can vary factors such as porosity, fracture conditions, density, and possible material inside the spaces, then calculate the behavior each candidate interior should produce. The logic is similar to examining an object sealed inside a box by observing how the box responds when gently disturbed. A heavy, tightly packed object would influence the response differently from a lighter or loosely arranged one. The comparison cannot reveal every detail, and several arrangements may behave similarly. Yet careful measurements can eliminate possibilities that do not fit. On Mars, the box is the crust, and naturally generated vibrations provide the disturbance. Earth offers a limited practical comparison. Seismic and related geophysical methods can help investigate groundwater without exposing every underground layer. Water changes the physical behavior of porous or fractured rock, so measurements made at the surface can help constrain what may occupy hidden spaces. The Martian investigation follows the same broad reasoning, but with far less direct access and only one seismic station. The analogy explains the method. It does not make the two settings identical. To manage the large number of possible interiors, researchers use statistical inversion. An inversion starts with the observed effects and works backward toward possible causes. Instead of drawing one preferred picture first, scientists allow many combinations of properties to be tested. Each combination predicts measurements. Those predictions can then be compared with what InSight and other observations actually recorded. Models that reproduce the data poorly lose support. Models that fit more of the observations gain support. The result is not simply a winning answer and a set of impossible ones. It is a distribution showing which combinations agree better with the available evidence and which remain less likely. This allows uncertainty to remain visible rather than being hidden behind a single diagram of the interior. Seismic information supplies only part of the constraint. Gravity also responds to how mass is distributed. Two candidate crusts might produce similar seismic speeds while containing different amounts or arrangements of dense material. If one candidate conflicts with the local gravity information, its seismic match is not enough to save it. A model that agrees with both types of measurement is harder to achieve and therefore more informative. This combination is essential because many internal properties can trade places inside a calculation. A change in porosity might partly imitate a change in mineral composition. A different temperature could alter the physical response. Changing what fills the pores may shift the predicted speeds again. Seismic and gravity constraints approach these unknowns from different directions, reducing the room in which misleading combinations can hide. Even then, the reconstruction remains a model. Scientists are not coloring a known map. They are identifying ranges of internal conditions that remain compatible with the measurements. The best supported model is the one that explains the evidence with the strongest overall agreement under the assumptions being tested. If those assumptions change, or if a material was not included among the candidates, the ranking may also change. This is why language matters. A result can show that one composition best explains existing data without showing that every alternative has been eliminated. It can provide strong evidence for a poor material without directly detecting a sample of that material. The difference is not a weakness added after the discovery. It is part of what the discovery scientifically means. By joining travel times, signal behavior, rock physics, statistical comparison, and gravity, researchers could turn InSight's tiny surface movements into a constrained view of buried structure. They could ask which kinds of fractured rock were consistent with the data and what might occupy the spaces inside them. Most possibilities would not fit equally well. When this process was applied beneath Elysium Planitia, one depth range behaved in a particularly important way. The measurements pointed toward a middle section of the crust, with properties that demanded a closer comparison among dry rock, ice, minerals, and liquid-filled fractures. The method had established how the candidates would be tested. The hidden layer would determine which candidate rose above the rest. The search now moved downward beneath Elysium Planitia, but it did not begin with water. It began with a layered question. If the crust changed with depth, each interval had to be treated according to its own measured properties. Conditions near the surface could not simply be extended downward, and a deep interpretation could not automatically describe the rock above it. The upper part of the crust provided the first contrast. Evidence from the InSight region indicated that roughly the first 5 kilometers were dry. This did not mean that every grain contained no trace of water, or that all of Mars shared the same structure. It meant that the available geophysical evidence did not require a substantial liquid-filled zone in that shallow interval. That result matched the visible character of modern Mars. The surface is cold, exposed, and dry. Ice can survive in protected settings, but stable liquid across open ground is another matter. If a large liquid reservoir remained beneath InSight, The measurements suggested that it did not begin close to the lander. Scientists had to follow the inferred structure farther into the crust. The important change appeared much deeper, between about 11.5 and 20 kilometers below the surface. This was the middle crust considered in the study. No drill had reached it, and no camera had recorded it. Its properties were constrained through seismic velocities, gravity information, and the rock physics comparison already established. Depth matters because pressure and temperature change as the crust descends. The history of the rock also matters. Mars built much of its crust through igneous processes, in which molten material cooled and became solid rock. Over time, that rock could be broken by impacts, internal stresses, and other parts of the planet's history. The resulting crust would not need to be a seamless block. It could contain cracks and pore spaces capable of holding another material. Researchers therefore tested a fractured igneous crust rather than imagining one smooth, empty layer. The solid framework supplied part of the model. The amount of pore space supplied another. What occupied that space supplied a third. Each choice altered the density and the way the model responded to compressional and shear motion. A dry version provided one candidate. If the pores and fractures contained little material, the rock would have one range of physical properties. Ice offered another candidate, because frozen water inside the spaces would change the response. Mineral-filled pores supplied further possibilities. Liquid water created a different combination again. The task was to determine which versions could reproduce the actual measurements together. This is where the earlier distinction between several forms of evidence became decisive. A candidate might approach one seismic speed while missing another. It might provide a reasonable wave response but conflict with the local gravity constraint. It might require a combination of porosity and pore material that did not fit the larger set of measurements. The preferred interpretation had to survive these comparisons as a whole. The comparison also had to respect ranges rather than pretend every property was known exactly. The measurements carry uncertainty, and the candidate rocks can be represented by more than one permitted density or fracture pattern. A useful result, therefore, does not depend on one perfectly chosen set of numbers. It asks whether a family of liquid-bearing models repeatedly occupies the region of strongest agreement, while other tested families struggle to satisfy the same combined limits. This approach turns uncertainty into part of the evidence. Wide uncertainty would allow many unlike interiors to remain plausible. Tighter overlap among seismic, gravity, and rock physics constraints removes more possibilities. The preferred answer becomes meaningful not because the model looks convincing in an illustration, but because it survives a comparison designed to expose disagreement. Its remaining uncertainty can then be stated openly, without erasing the fact that the candidates did not perform equally well. That ranking, rather than a direct view, forms the foundation of the proposed liquid layer. In the original analysis, fractured igneous rock, with its available pores and cracks saturated by liquid water, provided the best explanation for the mid-crustal data. The word saturated has a specific role here. It means that liquid occupies the connected pore space considered by the model. It does not mean that the entire layer is made of water. The rock remains the dominant physical structure, while the liquid exists within its fractures and pores. This result creates a very different image from a buried sea. Imagine a vast thickness of rock, crossed by spaces too small or scattered to resemble an open chamber. Water inside those spaces can still add up to a large quantity because the rock extends across a large volume. At any single point, however, the material would be rock-containing liquid, not a person standing beside an underground shoreline. The model also explains why the shallow dryness and deeper liquid possibility can exist together. The upper crust and middle crust occupy different physical settings. A dry interval above does not rule out liquid farther down, just as liquid at depth would not make the modern surface wet. The separation is part of the proposed structure. Dry rock near the top, followed by a deeper interval whose measured behavior is better matched when liquid fills fractures. At the relevant depth, the proposed water could remain liquid under conditions unlike those at the surface. The study did not require open lakes or sunlight. It required the physical properties of fractured rock and its pore contents to match the geophysical data. The conclusion therefore arose from the behavior of the layer, not from an assumption that ancient surface water must still exist somewhere. That distinction protects the investigation from circular reasoning. Scientists did not begin by declaring that the missing water had to be in the middle crust and then force the measurements to agree. They compared candidate materials through the inversion. The ancient water mystery made the liquid result important, but the geophysical fit was the reason it emerged as the preferred answer. The strength of the conclusion depends on that wording. The data are best explained by a particular model under the tested assumptions. This is stronger than saying that water is merely an attractive possibility. It means the liquid-bearing model performed better within the comparison. But it remains different from recovering a sample, drilling into the layer, or obtaining an independent image of water across the region. One location creates another boundary. Insight listened from Elysium Planitia. The seismic paths did not form a complete three-dimensional survey of the Martian crust, and the gravity information did not map every deep fracture across the planet. The result directly describes what is compatible with measurements near the lander and with the paths represented in the analysis. Mars may not be uniform. Its crust formed through a long history, and different regions can have different thicknesses, fracture patterns, temperatures, or mineral structures. A water-bearing interpretation beneath one site cannot demonstrate that the same interval exists everywhere else. Even if the local result is correct, the connected spaces could become fewer, drier, or differently filled with distance. The single station limitation also remains active within the region itself. Researchers can constrain ranges of properties, but they cannot point to every fracture. The inversion represents a set of possible conditions able to explain the observations. It simplifies a complicated crust into properties that can be tested. That is necessary for the calculation, yet any simplification leaves details unresolved. Still, the result provides a meaningful local payoff. The unusual mid-crust was not consistent with all candidate interiors equally. When seismic and gravity evidence were examined together, liquid-bearing fractured igneous rock rose above the alternatives in the original study. Mars had supplied a signal that looked less like completely dry stone and more like rock, whose internal spaces contained liquid. The depth of the layer gives this possibility a direct connection to the ancient water problem. Surface water could vanish from view while some portion moved into a protected crustal setting. The measurements do not trace individual drops from an ancient river into the modern middle crust, so they cannot prove that exact history. But they identify a possible present destination with the scale to matter. That last point changes the question again. Finding a preferred liquid-bearing model beneath one lander is scientifically important, but the title promises something enormous. The local layer becomes enormous only through an additional step. Researchers must estimate how much pore space it contains, how fully that space may be occupied, And what would happen if similar conditions continued beyond Elysium Planitia? That step is both powerful and dangerous. It can translate an invisible fraction of water inside rock into a volume large enough to compare with ancient Martian oceans. It can also tempt the listener to forget that the calculation begins at one site. The measurements had identified the preferred local interpretation. The next question was how far that interpretation could responsibly be extended across a planet. The measurements beneath InSight described a local problem. The title, however, points towards something much larger. Moving from one to the other requires an extrapolation, a controlled calculation that asks what the local interpretation would mean if comparable conditions existed across a far greater area of Mars. The calculation begins with rock, not with an ocean. Between roughly 11.5 and 20 kilometers beneath the landing region, the preferred model contains fractured igneous material. The layer has a large physical volume, but most of that volume is solid. Water would occupy only the pores and cracks within it. The amount of liquid, therefore, depends on how much space the rock contains and how fully that space is filled. Porosity describes the fraction of a material made up of open space. A solid block with almost no pores can hold little fluid inside it. A heavily fractured rock can provide much more room, even though the rock still appears solid on a large scale. Multiply that available space through several kilometers of crust, and a small fraction can become a substantial volume. Saturation adds another part of the calculation. Pore space may be empty, partly filled, or filled throughout the connected spaces represented in a model. The original preferred interpretation placed liquid water through the available fractures strongly enough to reproduce the measured physical properties. The more of that pore volume assigned to liquid, the larger the inferred inventory becomes. Thickness matters as well. A thin water-bearing band and a layer extending through several kilometers of crust could have the same porosity but hold very different totals. The mid-crustal interval beneath InSight supplied the depth range used in the interpretation. That local vertical structure then became one dimension of the larger estimate. The final and most uncertain dimension is area. How far does a similar layer extend sideways? InSight cannot answer that globally. Its seismic paths and nearby gravity constraints do not form a planet-wide survey. Researchers therefore cannot add measured water beneath every region. They can only ask what the total would be if the structure near Elysium Planitia were representative of much more of Mars. The phrase "if representative" carries the weight of the entire scale claim. It means that the relevant thickness, pore space, and liquid content beneath one region are assumed to occur widely enough for a global calculation. It does not state that this similarity has been observed. It creates a scientifically useful scenario whose result can be compared with other estimates of the Martian water budget. Under that condition, the total becomes enormous. The inferred amount of liquid would be sufficient, if removed from the crust and spread evenly over the surface, to cover Mars beneath a layer between 1 and 2 kilometers deep. That image is powerful because it converts a hidden volume into a scale the mind can picture. Instead of imagining water divided among countless small spaces inside rock, imagine gathering every part of it, bringing it to the surface, and distributing it evenly from pole to pole. Every crater, plain, volcano, and basin would lie beneath the same imaginary layer. The depth of that layer expresses the total amount of water. Scientists call this a global equivalent layer. It is a unit of comparison, not a map. It answers a volume question. If all the water were placed into one evenly distributed layer, how deep would that layer be? The same method allows different reservoirs or past estimates to be compared without claiming that the water ever existed in that exact shape. A global equivalent layer also prevents familiar surface geography from distorting the comparison. A real ocean would gather in low basins rather than cover mountains and plains evenly. Its depth would vary from place to place. By removing those differences, the calculation reduces the problem to total water divided by total surface area. The resulting depth is imaginary, but the volume it represents can still be compared consistently with other proposed reservoirs. It is therefore best understood as a common measuring scale, much like converting objects of different shapes into the same unit of mass. The range between 1 and 2 kilometers also matters. It shows that the calculation does not produce one perfectly exact total. The allowed properties of the local model cover a range, and those differences carry forward when the volume is estimated. Reporting a range preserves that uncertainty. Choosing only the larger value would make the result more dramatic but less complete. Choosing only the smaller value would hide how much water remains compatible with the preferred model. Both limits belong to the same conditional interpretation. This creates three separate questions that must not be blended together. First, do the local measurements favor liquid inside fractured rock? Second, what local volume follows from the permitted porosity and saturation? Third, how much of Mars shares a comparable layer? The first question is constrained by the InSight region data. The second is calculated from the model. The third remains largely open. The ocean scale figure answers what follows if the third question receives the broadest possible continuation, not whether that continuation has already been observed. The difference between capacity and confirmed inventory offers another useful guardrail. The model shows that a widespread layer with these properties could contain an enormous total. It does not show that every pore across Mars is present or filled. The calculation establishes what the proposed structure is capable of storing under the stated assumptions. Establishing how much water exists planet-wide would require evidence from locations that InSight could not constrain. The distinction is essential. A 1 to 2 kilometer global equivalent layer does not mean that a real ocean sits 1 or 2 kilometers below the ground. It does not mean the proposed water-bearing rock is itself only that thick. It does not identify coastlines, currents, empty chambers, or a single connected body. The number describes an imagined surface depth created from a total volume that may actually be divided through the crust. This is why two different measurements can be confused. The proposed mid-crustal interval lies many kilometers beneath the surface and extends through a particular vertical range in the local model. The global equivalent layer is something else entirely. One describes where the possible water-bearing rock begins and ends beneath InSight. The other describes how deep the water would be after an imaginary extraction and redistribution. Once this difference is clear, the estimate can be compared with the ancient water problem. Geological evidence indicates that Mars once supported rivers, lakes, and possibly large standing bodies of surface water. Their original total cannot be known with perfect precision, and estimates differ according to the evidence and period considered. Yet the conditional mid-crustal inventory is comparable to, or may exceed, some proposed volumes for those ancient surface waters. That comparison creates the central payoff. A major part of the water that appears missing from the modern surface may not have escaped the planet. Some could have entered the crust and remained there. If the local model is correct and broadly representative, Mars may have moved an ocean-scale inventory from a visible surface system into an invisible rocky one. The idea changes the water ledger established earlier. Atmospheric escape still removed part of the inventory. Ice and hydrated minerals still hold other portions. The deep crust would not replace those destinations. It would add another reservoir, possibly large enough that models of Martian history could no longer treat deep liquid water as a minor remainder. Yet every stage of the estimate can change. If the rock elsewhere has less pore space, it holds less water. If fewer fractures are filled, the inventory falls. If the suitable layer is thinner, the total decreases. If it exists only around Elysium Planitia or in scattered regions, multiplying it across the planet would greatly overstate the volume. The opposite possibilities also cannot be mapped from one station. Other regions might contain different fracture networks or layer thicknesses. But without measurements there, increasing the estimate would be no more justified than decreasing it. The responsible result is not a claim that the exact same reservoir surrounds Mars. It is a conditional scale derived from the region scientists could constrain. This conditional form does not make the number meaningless. Extrapolation is often how a local physical result is tested for its larger consequences. The key is to show the assumption beside the result. The calculation says that the local interpretation has enough capacity to matter on a planetary level. Future observations must determine how much of the planet actually shares those conditions. The scale can also be understood without pretending that the water is evenly distributed. Consider a thin fraction of pore space repeated through a huge body of crust. Each individual fracture contributes little. A cubic section of rock may contain far more stone than water, but the Martian crust spans an entire world. When small contributions are added through a layer thousands of meters thick and potentially spread across vast areas, their combined volume can rival a surface ocean. This is the counterintuitive heart of the finding. Something does not need to form one open body to become enormous. A reservoir can be dispersed and still have planetary importance. The quantity arises from multiplication, pore space within rock, repeated through thickness, then extended across area. Change any factor and the answer changes. But under the representative scenario, the total reaches the scale promised by the headline. The estimate also explains why the discovery emerged from calculations rather than from a dramatic individual signal. No single marsquake carried the number 1 to 2 kilometers. The number was produced by connecting the preferred local material model with the possible volume of the crust. It is a consequence of the interpretation, not a raw measurement written directly into the waveform. That difference creates a clear hierarchy of confidence. InSight recorded ground motion. Researchers used those measurements and gravity information to constrain local mid-crustal properties. A liquid-bearing fractured rock model gave the preferred original explanation. Extending that model across Mars produced the ocean-scale estimate. Each step depends on the one before it, and each new step adds an assumption. The scale claim should therefore always remain attached to its condition, if the region beneath InSight is representative. Remove that phrase, and a scenario becomes a declaration of global fact. Preserve it, and the result remains both extraordinary and accurate. One lander may have detected evidence of a local structure whose planetary continuation could store more water than the ancient surface once displayed. At this point, the answer appears almost complete. NASA's data revealed a possible reservoir with an ocean-scale volume. But the familiar word ocean still carries the wrong physical picture. It suggests open water, a continuous surface, and a place into which something could descend or sail. None of those features follows from the calculation. The enormous quantity may exist, if the interpretation is correct, in a form that looks almost nothing like an ocean. To understand what was actually proposed, the investigation must return from the planetary total to the spaces inside the rock. An ocean is usually understood as open water. It has a surface separating liquid from air, a floor beneath it, and connected space through which water can move. That image is useful for describing the global equivalent volume, but it is not the physical structure proposed beneath Mars. The calculation creates an imaginary ocean only after removing the water from the crust. Inside the actual model, rock remains everywhere. The middle crust is made primarily of fractured igneous material. Liquid would occupy some of the small spaces within that material. Pores between parts of the rock, narrow cracks, and larger fractures created during the crust's long history. The water would be part of a mixed rocky system, rather than a separate layer resting above or below it. The individual spaces may be extremely small compared with the full depth interval. Some could connect with neighboring cracks. Others could end inside the rock. Several water-filled regions might be separated from one another by material with little open space. The model constrains general physical properties. It does not trace the route of every fracture or show that the proposed liquid forms one continuous network. This creates a scale that is difficult to picture. At the level of one piece of rock, only a fraction of the material may be liquid. Across a crustal layer several kilometers thick, that fraction is repeated through an immense volume. Add enough small spaces together, and the total becomes comparable to an ocean, even though no part of the reservoir needs to resemble open sea. A familiar sponge offers a limited analogy. A wet sponge can contain a noticeable amount of water while remaining mostly solid material. The liquid exists throughout spaces inside its structure, rather than as a separate pool. Martian crust would not behave exactly like a household sponge, and its pores would be controlled by rock, pressure, fractures, and depth. The comparison serves only to separate total water content from an open body of liquid. The absence of an open chamber changes nearly every intuitive feature of an ocean. There may be no shoreline because there is no broad surface where water ends and empty space begins. There may be no current joining distant regions. There may be no single depth that describes the reservoir itself. Moving through it would mean moving through rock, not moving freely through liquid. Connectivity is therefore one of the most important unknowns. If fractures join across useful distances, water may be able to move slowly through parts of the crust. If they are isolated or blocked, the liquid could remain divided into many separate pockets. The seismic model does not provide a complete plumbing map. It indicates physical conditions compatible with liquid-filled space, not how easily that liquid travels from one location to another. The difference between storage and flow is useful here. A rock volume may contain water even when the liquid cannot move easily between neighboring spaces. Total inventory asks how much liquid is present. Connectivity asks whether those separate amounts form pathways. Permeability asks how readily movement could occur through those pathways. The outline of the findings supports the first question conditionally, but it does not settle the other two. An ocean-scale total could therefore be divided among regions that do not communicate in any simple or rapid way. The proposed depth makes direct access another problem. The zone begins about 11.5 kilometers below the surface and extends toward 20 kilometers. Even on Earth, drilling to comparable depths is an extreme technical challenge. A future crew on Mars would face that depth while operating on another planet, with limited equipment, power, replacement parts, and knowledge of the exact target below. This means the water should not be presented as a convenient supply for early human explorers. Its possible volume may be enormous, but volume and availability are separate questions. A small deposit close to the surface could be more useful than a much larger inventory sealed kilometers down. The proposed mid-crustal water may matter greatly to planetary history while remaining beyond practical near-term extraction. Access would require more than reaching the correct depth. A drill would need to enter rock that actually contains suitable fractures, because a broad model does not identify a guaranteed point target. Equipment would then have to operate under the conditions there and recover liquid from within the solid structure. None of those engineering steps follows automatically from the estimated volume. The headline measures possible abundance, while practical use depends on location, concentration, connection, and recovery. Treating those questions separately prevents a scientific water estimate from becoming an unsupported promise of an easy Martian resource. A reservoir can therefore be enormous in the mathematics of total volume, while remaining fragmented, remote, and effectively unavailable to any mission built with present capabilities on the surface. The depth also prevents scientists from treating the water as a known environment. The model does not directly measure its chemistry. It does not show which minerals have reacted with it, what substances may be dissolved within it, or whether the composition changes across the region. A liquid can exist and still be unsuitable for drinking, equipment, or biological activity. Temperature and pressure must also remain within the boundary of the inference. The preferred rock physics model permits liquid at the relevant depths, but it does not provide a direct reading from a probe placed in the reservoir. Conditions could vary across the layer. The long-term stability of the water, its movement, and its history inside the crust remain questions rather than completed measurements. Yet the possibility of persistent liquid water naturally raises a deeper biological question. On Earth, life can exist beneath the surface in environments separated from sunlight. That comparison shows why researchers care about deep liquid water as more than a resource. Where liquid, usable chemistry, suitable temperatures, and enough time occur together, an environment may be considered potentially habitable. Potentially habitable does not mean inhabited. InSight carried no instrument into the proposed layer. It collected no water sample and detected no organism there. The seismic measurements did not reveal cells, metabolism, organic remains, or a biosignature. They addressed physical properties of the crust. Any connection to present life begins only after the liquid interpretation and adds further conditions that have not been tested. This distinction is especially important because the phrase "water on Mars" carries emotional weight. Liquid water is connected with life as humans know it, but it is only one requirement among several. A location can contain water while lacking usable energy, suitable chemistry, stability, or other conditions needed by living systems. The discovery cannot be turned into evidence of biology without crossing several unsupported steps. The careful conclusion is narrower and still significant. If liquid fills fractures in the Martian middle crust, then a setting with at least one major requirement for habitability may exist far below the hostile surface. That possibility would guide scientific questions about future exploration. It does not allow the documentary to announce a living underground Mars. Returning to the physical image helps maintain this boundary. The lander sat above kilometers of dry and fractured material. Farther down, according to the preferred interpretation, some internal spaces may contain liquid. The total could become vast when extended across a large area, but any individual part would remain enclosed by rock under conditions no mission has directly sampled. The phrase "hidden ocean" therefore captures scale while distorting structure. It encourages viewers to imagine a clean discovery, a blue body beneath red ground, waiting behind a final wall of stone. The real proposal is less visually simple. It is a statistical and physical inference about fluid inside a complicated crust whose exact geometry remains unknown. That more accurate picture does not reduce the discovery. In one sense, it makes the survival of so much possible water more remarkable. The water need not remain in a familiar basin. It may have entered a network of protected spaces, becoming almost invisible to surface exploration while continuing to influence the physical behavior of the rock. But correcting the image also exposes the next scientific problem. Once an open ocean has been replaced by liquid-filled fractures, scientists must ask whether liquid is the only material able to create the measured behavior. The original analysis preferred water saturation, but a preferred model can be tested by changing its assumptions and examining the full range of results. The discovery had survived the first comparison among candidate interiors. It now had to survive a more difficult question. Did InSight's evidence truly require the Martian middle crust to be saturated with water? Or could another arrangement of rock and pore material produce a similar signal? The original result was important because the water-saturated model performed best within the comparison. But scientific strength does not come from leaving a result untouched. It comes from allowing other researchers to examine the assumptions, calculations, and uncertainty behind it. A conclusion that survives careful challenge becomes stronger. A conclusion that changes under challenge becomes more accurate. The first question concerned the word saturated. In the preferred model, liquid occupied the connected pore space strongly enough to match the combined physical constraints. Public summaries could easily turn that into a fully confirmed crust, filled throughout with water. The statistical result, however, contained a range of possible saturation levels rather than one directly measured percentage. In 2025, a peer-reviewed critique returned to that statistical distribution. Its authors argued that the InSight results did not strictly require a water-saturated middle crust. Lower levels of saturation remained permitted within the range of solutions. The original model could still favor substantial liquid, but the data did not force the conclusion that nearly all relevant pore space had to be filled. This is a narrow disagreement with large consequences for the headline. If the saturation is lower, the total water inventory becomes smaller. The planet-wide extrapolation also changes, because the calculation multiplies the local liquid fraction across a huge crustal volume. A difference inside pores beneath one site can become a major difference after being extended across Mars. The critique did not show that no liquid water exists. It did not replace the seismic record with a direct sample of dry rock. It examined how the existing result should be read. Its central point was that the allowed statistical range supported more than the most dramatic end of the interpretation. The word require is especially useful for understanding the debate. A model may be favored because it occupies more of the best-fitting range, yet the evidence may still allow other values. Saying that water saturation is not required means that acceptable solutions are not confined to near-complete filling. It does not mean that saturated solutions vanished from the analysis. The difference lies between what the data prefer under one reading and what they absolutely exclude. Careful narration must preserve both parts of that distinction. That distinction prevents a common mistake. Scientific criticism is not always a contest in which one paper survives and another is discarded. The original study established a preferred water-bearing explanation under its modeling choices. The critique showed that the degree of saturation was less firmly required than a simple summary might suggest. both contribute to a more careful statement of what the measurements permit. A separate assessment in 2025 examined another part of the problem: the material assumed to occupy or alter the pores. Fractured igneous rock does not remain unchanged under every possible history. Minerals can transform, and pore spaces can contain materials whose physical effects may overlap with those expected from liquid water. If the starting crust and its later alteration differ from the original assumptions, another model may reproduce part of the observed behavior. The same discipline applies to transformed minerals. If a different assumed crustal history changes the predicted density or rigidity, part of the signal previously assigned to liquid may receive another explanation. But every added possibility introduces its own assumptions. The question is not whether an alternative can be imagined. It is whether that alternative matches all relevant measurements, remains physically consistent, and performs well enough to challenge the original ranking. At present, the alternatives broaden uncertainty more clearly than they deliver a final replacement. The honest outcome is therefore a ranked set of explanations, not a choice between confirmed water and confirmed dryness beneath all of Mars. This does not create one proven dry alternative. It widens the comparison. A mineral-filled or transformed crust must still agree with the seismic velocities, density constraints, and other physical limits. The proposed material also has to be plausible within the conditions being assumed. Introducing an alternative is not enough. It must survive the same demand for combined agreement. The result is a problem of model uniqueness. Several interiors may occupy overlapping regions of the available evidence. One may fit better under one set of rock properties, while another becomes more competitive when the assumed mineral composition changes. The measurements restrict the possibilities, but they may not reduce them to one answer. This is exactly the kind of uncertainty expected when scientists investigate a layer that cannot be sampled. Every interpretation connects measured signals with laboratory knowledge, physical models, and assumptions about an inaccessible crust. Changing a justified assumption can reveal how dependent the conclusion is on that choice. The exercise does not erase the data. It maps the boundary of what the data can establish. Several findings remain stable across the disagreement. InSight recorded the seismic events. The relevant wave speeds and gravity information require an explanation. The middle crust beneath the investigated region has physical properties that are not described equally well by every simple candidate. Fractures, pore space, density, and the material history of the rock matter to the result. What changes is the level of certainty assigned to liquid water. The strongest safe conclusion is not that an underground ocean has been confirmed. It is that liquid-bearing fractured rock provides a serious and potentially powerful explanation, while lower saturation or other pore and mineral conditions remain possible. The local anomaly is supported more strongly than any single global interpretation of it. The alternatives also remain models. A critique cannot look into the crust any more directly than the original inversion. It can demonstrate that another range of conditions fits, or that the original conclusion was not uniquely required. It cannot identify the actual pore contents without additional evidence. A dry or mineral-filled possibility should therefore not be promoted from alternative to fact. Resolving the uncertainty requires measurements that approach the problem from new positions or through a different physical method. A network of seismic stations could record the same events from several locations, improving the reconstruction of sources and paths. Measurements from other regions could test whether the Elysium Planitia structure continues across Mars or changes sharply with geography. Another independent method could provide a constraint that does not depend on exactly the same assumptions. Direct sampling would be most decisive, but the depth makes that prospect remote. Until stronger evidence arrives, the responsible interpretation must preserve both the preferred water result and the alternatives that remain compatible with the observations. This restraint does not empty the discovery of meaning. The original analysis identified a way that Mars could store an ocean-scale inventory. The critiques showed where confidence should narrow: the exact saturation, the uniqueness of liquid as the pore material, and the global continuation of the local structure. The central mystery became more precise rather than less interesting. Science had therefore turned one dramatic statement into several graded conclusions. Ground motion was observed. Mid-crustal properties were inferred. Liquid water was preferred within the original rock physics comparison. Near-complete saturation was challenged. Planet-wide volume remained conditional. Present life was never detected. Each claim belonged at a different level of confidence. The investigation could have ended at that boundary, with water remaining an unresolved interpretation beneath one landing site. But InSight's archive contained signals that traveled much deeper than the proposed reservoir. Those waves did not settle the pore contents of the middle crust. Instead, they revealed that another familiar assumption about Mars was also incomplete. The mantle below was not smooth, simple, or fully mixed. The uncertainty in the middle crust concerned what occupied tiny spaces inside rock. Deeper signals revealed a different kind of problem. As seismic energy traveled through the Martian mantle, parts of it behaved as though the material along the path was not smooth or uniform. The waves arrived carrying signs of disruption on a scale far larger than pores. Researchers examined high-frequency signals from selected marsquakes and impacts that sent energy deep through Mars. High-frequency details can be sensitive to relatively small irregularities along a path. Instead of producing patterns expected from a simple, evenly mixed mantle, parts of the recorded energy arrive delayed, scattered, or scrambled. A wave can become scattered when it encounters regions whose physical properties differ from the surrounding material. Part of the energy continues along one route, while other parts are redirected or delayed. By comparing the observed disturbance with models of possible interiors, researchers can estimate the kind and size of irregularity needed to produce it. Different sizes of irregularity affect seismic energy in different ways. A feature much smaller than the relevant wave detail may have little distinct influence, while larger contrasts can disrupt the signal more strongly. Researchers can therefore compare how several frequencies are delayed or scattered and test which distribution of internal domains reproduces the pattern. This does not locate every feature individually. It constrains a population of heterogeneities, allowing their general scale and abundance to be inferred from the combined behavior of the waves. The result did not support a mantle that was identical everywhere. It pointed toward heterogeneities, regions with different composition or physical properties distributed through the deeper planet. Some of these inferred domains may be as large as roughly 4 kilometers across. On the scale of human engineering, that is enormous. On the scale of a mantle, it is a pattern embedded within a much larger body. The word lump provides an easy description, but a dangerous image. It can sound as though separate boulders are floating freely inside molten material. That is not what the seismic evidence directly shows. The inferred features are domains whose density, composition, or other physical behavior differs enough from their surroundings to disturb passing waves. Their boundaries may be irregular, and their exact shapes are not directly known. The evidence, therefore, concerns contrast, not a photograph. A wave responds when the material ahead changes. From that response, researchers infer that the mantle contains patches or regions unlike the average material around them. They cannot hold one of those regions, identify every mineral within it, or draw its complete outline. The next question is how a planet acquired such large internal differences. Researchers connected the pattern with the violent environment in which Mars formed. Early in the solar system's history, large bodies collided frequently. Mars was struck by objects capable of releasing extraordinary amounts of energy into its crust and mantle. A giant impact would not simply leave a crater at the surface. Its energy could melt major portions of the early crust and mantle, creating broad regions of molten material. The impact could also drive a mixture of foreign material and Martian debris into the planet. When those regions later cooled, they would not necessarily match the composition of the mantle around them. If repeated impacts created many such domains, their sizes might retain a pattern connected with the collisions that produced them. The inferred distribution of Martian mantle heterogeneities is consistent with the idea that ancient impacts placed differently composed material at depth. The planet's interior may therefore contain physical traces of events that occurred about 4.5 billion years ago. This interpretation turns the mantle into a historical record. Surface craters can be erased, buried, or changed. Material inside a planet can also mix until an original difference disappears. Yet Mars appears to have preserved internal contrasts long after the violent period that may have created them. The reason lies in how Mars changes its interior. Earth continually moves large plates across its surface. Material descends, returns, and becomes recycled through a globally active system. This movement helps mix parts of Earth's mantle across long periods. Mars does not operate with the same global pattern of plate tectonics. Its outer shell behaves as a stagnant lid. A stagnant lid does not mean that nothing moves beneath the surface. Heat can still travel, mantle material can still change slowly, and volcanic activity can occur. It means that the outer shell is not divided into an Earth-like global network of plates repeatedly carrying material down and bringing other material upward. Without that large recycling system, the Martian mantle could mix less completely. Its internal movement may be too slow or limited to erase every compositional boundary produced near the beginning of the planet's history. Regions created by impacts could be stretched or altered while still remaining different enough to scatter seismic waves billions of years later. The survival of a contrast depends on whether later movement blends it into the surrounding mantle. Imagine placing differently colored material into something that is stirred. Fast, repeated stirring eventually weakens clear boundaries. Slow and incomplete stirring can leave patches recognizable for far longer. The mantle is not literally a colored liquid, but the comparison explains the preservation problem. Mars needed enough internal movement to evolve, yet not enough mixing to erase every difference planted during its earliest collisions. Preservation across 4.5 billion years creates the section's deepest scale change. InSight operated for only a few years. An individual seismic signal crossed Mars over a short interval. Yet the irregularities influencing that signal may have formed when the planet itself was young. A recent measurement can therefore carry information from the earliest era of Martian formation. This is independent of whether the middle crust is fully saturated with water. The mantle result uses different signals, depths, and physical effects. The uncertainty of one interpretation does not remove evidence for the other. InSight's larger legacy is not tied to a single proposed reservoir. Its archive exposed complexity across several layers of the planet. The mantle result also corrects another familiar picture of Mars. A planet without Earth-like plate tectonics can appear internally simple or inactive. But preservation is not simplicity. Mars may contain a more visible record of its early disorder, precisely because it did not recycle and erase that record as completely as Earth. The inferred heterogeneities help constrain how efficiently the mantle has mixed and how its material has moved over time. If large differences remain, models of Martian evolution must allow them to survive. The seismic signals therefore connect present structure with long-term interior behavior, not merely with ancient impacts. This preserved structure gives Mars a different scientific value from a planet whose interior has been recycled more thoroughly. The heterogeneities may keep information about the kinds of material involved in early impacts, the energy those events delivered, and the later pace of mantle mixing. InSight cannot recover all of that history alone. It shows that the record may still exist, creating physical limits that future models of the young planet must respect. Rather than erasing uncertainty, the discovery identifies a surviving structure whose origin must be explained by any successful account of Mars's long internal evolution from beginning to present. Still, the impact interpretation remains an inference. The size pattern and physical context support it, but InSight did not identify the exact object that struck Mars or prove the origin of every internal domain. Other details of the mantle and the detection method can affect how the scattering is understood. The responsible claim is that ancient impact remnants offer the best supported explanation, not that intact impactors have been mapped. This uncertainty preserves an important boundary. The delayed and scattered signals are observations. Kilometer-scale heterogeneities are inferred from those observations. Their compositional nature is a strong interpretation. Their origin in giant early impacts is a further explanation supported by the distribution and Martian evolution. Each step adds meaning and also adds assumptions. Even with those limits, the discovery changes the planet's interior from a smooth diagram into a preserved landscape of differences. Mars may hold ancient material domains scattered through its mantle, left behind by collisions that shaped the early world. The lander did not see them. It heard waves lose their clean shape while passing through them. Once the mantle could no longer be assumed uniform, another result required reconsideration. Earlier seismic models had treated a deep reflecting boundary as the edge of the metallic core. But a heterogeneous mantle can contain additional layers, including material soft or molten enough to redirect waves. The boundary researchers thought they understood might not mark the core at all. The first seismic estimate of Mars's core appeared to provide a clean answer. Waves reflected from a deep boundary, and researchers interpreted that boundary as the place where the solid mantle ended and the liquid metallic core began. Under a model with a compositionally uniform mantle, the core radius was estimated at approximately 1,830 kilometers. That made the Martian core surprisingly large. Because the total mass of Mars was already constrained, a larger core had to be relatively low in density. Iron alone could not explain that result. The model required a substantial amount of lighter elements mixed into the metallic liquid to reduce its average density. Light elements inside a planetary core are not unusual. The difficulty was the amount required by the large core model. It pushed the proposed composition toward levels that were hard to reconcile with other physical and chemical constraints on the materials from which Mars formed. The seismic boundary appeared clear, but the interior it implied created a new problem. Additional insight signals made the simple picture harder to maintain. Deep reflected waves supplied information about boundaries, while diffracted waves traveled along or through the lowest parts of the mantle. Their arrival times did not fit comfortably with every prediction of a uniform mantle resting directly on a large metallic core. Some energy appeared to move too slowly through the deepest region. The disagreement could not be repaired simply by changing the core. A wave approaching the center of Mars passes through the material above it first. If that lower mantle contains a slow, soft, or molten layer, the extra travel time changes where a reflecting boundary appears to be. A feature attributed to the top of the metallic core might instead belong to the mantle immediately above it. The apparent size of the core illustrates why identifying a boundary matters as much as measuring its depth. Seismic waves can reveal that a change exists, but the waves do not attach a material name to either side. That identity comes from testing complete models. If a solid mantle sits directly above liquid metal, the boundary has one meaning. If partly and fully molten silicate intervene, a reflection at a similar depth can represent a different transition, while the true metal boundary lies farther inward. In 2023, two independent studies developed this possibility. Both found evidence supporting a liquid or molten silicate layer above a smaller metallic core. Silicate is the rocky material associated with the mantle. At sufficiently high temperatures, some of that material can remain partly or fully molten even though the larger mantle above is solid. The two independent 2023 studies were valuable because they approached the deep structure with distinct combinations of seismic phases and physical calculations. Their convergence did not transform the molten layer into a direct sample, yet it reduced the chance that the idea depended on one isolated modeling choice. Both investigations found that a layered deep mantle and smaller core could account for observations that strained the earlier uniform model. Agreement between teams strengthened the mechanism while leaving exact dimensions open. The proposed basal layer is not a second metal core. It is deep mantle material, separated by composition and temperature from the mantle above it. In the models, the region can include a partly molten zone and a more fully molten silicate layer close to the metallic core. Estimates place the relevant thickness on the order of roughly 90 to 150 kilometers, depending on the study and model. This layered structure changes how seismic waves are interpreted. Shear motion cannot pass through fully liquid material in the same way it passes through a solid. A wave may reflect where the silicate becomes sufficiently molten, rather than where silicate finally gives way to metal. Compressional energy can travel through the slow molten layer, accumulate delay, and then interact with the deeper core boundary. The earlier boundary was therefore real as a seismic feature, but its identity could have been mistaken. What appeared to be the surface of the metallic core may have marked a transition within the deepest mantle. Once the molten silicate layer was included, the same broad observations could be explained with a smaller core beneath it. The revised metallic core radius fell to roughly 1,650 to 1,675 kilometers. This was a major change in planetary structure. The reduction was not caused by the core physically shrinking between measurements. It came from recognizing that part of the region previously counted as core could instead be molten rock above it. A smaller core must be denser to remain consistent with the known mass of Mars. That denser result reduces the amount of light material required in the metallic liquid. The composition becomes easier to reconcile with the physical and chemical limits that made the earlier low-density core difficult to explain. The new model therefore solves more than one problem at once. It improves the interpretation of the slow, deep seismic phases. It changes the location of the true core boundary. It produces a denser metallic core, and it reduces the need for an extreme mixture of light elements. Agreement across several constraints makes the layered interpretation stronger than a correction based on one signal alone. The molten region may also preserve another result of Mars's earliest history. When the young planet was extensively molten, materials could separate as the global magma ocean cooled. A deep layer enriched in iron and heat-producing elements may have collected above the metallic core. Its composition would help it remain dense and retain heat, allowing part of the basal mantle to stay molten long after most of the mantle solidified. This possibility connects present structure with planetary evolution. A chemically distinct basal layer would affect how heat moves between the core and mantle. It would influence estimates of how quickly different regions cooled and how the mantle moved over time. Because the history of the core is connected with the history of Mars's magnetic field, revising the deep thermal structure also changes how scientists reconstruct the planet's ancient magnetism. The same theme appeared in the mantle heterogeneities above. Mars did not mix into one simple, uniform interior. Ancient differences may have survived at several depths. Impact-related domains could remain scattered through the mantle, while material separated from an early magma ocean could remain concentrated near the core. The planet's lack of complete recycling preserved complexity that a smooth layered diagram had hidden. The core itself did not remain a finished picture. In 2025, another seismic analysis reported evidence for a solid inner core approximately 600 kilometers across in radius. This introduced a further boundary inside the metallic region. Rather than being entirely liquid, the core could include a solid center surrounded by liquid metal. Combined with the molten silicate interpretation, the deepest Mars becomes a sequence of physically different regions. A solid inner core may occupy the center. A liquid metallic outer core surrounds it. Above the metal lies a fully or partly molten silicate layer belonging to the mantle. Farther outward, the largely solid mantle contains preserved heterogeneities before giving way to the crust. This revision also changes the word liquid inside Mars. Liquid water in crustal fractures, molten silicate above the core, and liquid metal in the outer core are three very different substances under different conditions. They should never be merged into one image of a watery interior. Their shared ability to flow does not give them the same origin, composition, depth, or scientific evidence. Keeping them separate allows the planet's layered structure to remain clear. Each boundary affects waves differently, and each new layer increases the number of possible paths and interpretations. This is why the result must remain open to revision. InSight was one station. Only a limited number of seismic events sent clear energy through the deepest planet. Models must connect sparse paths with a complete internal structure. The solid inner core claim is therefore an important update, not the final word. Its approximate size, and even the details of the deepest states, will require testing with future seismic records. New stations could observe events from several angles and separate paths that one receiver must infer indirectly. Scientific self-correction is the central meaning of this sequence. The first core estimate was not careless. It was the best interpretation available under a simpler mantle model. Later signals and improved comparisons exposed a conflict. Researchers added a physically motivated layer, tested its consequences, and found that it resolved several problems while revising the core. The boundary did not disappear. Its meaning changed. What had been treated as the edge of liquid metal became evidence for molten rock above a smaller core. The correction revealed more structure, not less knowledge. It showed that a seismic reflection can be measured clearly, while the material creating it remains open to interpretation. Mars now appears complex from crust to center. A possible liquid-bearing zone lies within fractured mid-crustal rock. Kilometer-scale differences remain scattered through the mantle. A molten silicate layer may surround a denser metallic core, which may itself contain a solid center. No single cutaway image can express the different confidence attached to every part. That distinction prepares the final answer. InSight revealed several enormous possibilities and structures, but they are not all known in the same way. Some begin with direct ground motion. Others arise from strong seismic inference. Some depend on model choices, and one reaches planetary scale only through extrapolation. To state what NASA truly found, those levels must now be assembled without blending them together. The question in the title can now be answered, but only by separating what InSight measured from what scientists inferred. NASA placed the instrument on Mars and produced the seismic record. Research teams used that record, gravity information, rock physics, and statistical models to reconstruct possible conditions below. The enormous finding exists within that chain of evidence. InSight directly detected movement of the ground. More than 1,300 seismic events left patterns in arrival time, strength, frequency, and wave behavior. Some sources were linked with impacts seen from orbit. These observations are the firm foundation. They show that energy traveled through Mars and returned information shaped by the hidden interior. The instrument did not directly detect a substance. No waveform arrived labeled liquid water. No signal contained a photograph of an impact fragment or a molten layer. Those conclusions emerged because different internal structures would alter the waves in different ways, allowing researchers to test which explanations agreed best with the measurements. For the middle crust beneath Elysium Planitia, the original analysis found that fractured igneous rock containing liquid water provided the preferred explanation. The important interval lies between roughly 11.5 and 20 kilometers below the surface, beneath an upper region that appears comparatively dry. Water inside the model occupies pores and fractures rather than replacing the rock. This preferred interpretation is the title's primary answer. NASA's data allowed scientists to infer a possible reservoir whose total could be enormous. If the structure beneath InSight is representative of much of Mars, the liquid inside the middle crust could equal enough water to cover the planet between 1 and 2 kilometers deep after imaginary extraction and redistribution. That is the something enormous, not one visible object, but a possible ocean-scale inventory distributed through an immense volume of fractured rock. Every part of that sentence matters. Possible means the liquid interpretation is model-based. Ocean scale describes total volume, not physical shape. Distributed through rock corrects the image of a freestanding sea. And if representative preserves the assumption that turns one region into a planetary estimate, remove those qualifications, and the result becomes a different claim from the one the evidence supports. Saying that NASA discovered a global underground ocean would imply direct detection, known continuity, and a mapped body of liquid. InSight supplied none of those things. It supplied measurements whose preferred original explanation can produce a global ocean-scale total under a stated extrapolation. The phrase found beneath Mars must therefore be understood as a scientific reconstruction. NASA found a data set on the surface, years of recorded motion. Within that data set, researchers found patterns that simple interiors could not explain. The hidden structures are the causes that best account for those patterns under models. This difference between finding a signal and identifying its cause is why the result can be both a genuine discovery and an open scientific question. The water estimate remains the payoff because it reconnects the interior with the ancient surface. Channels and deltas show that water once moved. The seismic interpretation proposes that a portion may now occupy places cameras cannot reach. If representative, the crust could have stored rather than lost much of the inventory. Yet the connection is not a tracked journey from river to fracture. It is a possible solution linking two bodies of evidence across billions of years. The scientific challenges narrow the conclusion further. A 2025 critique showed that near-complete water saturation was not strictly required by the full statistical range. Lower saturation remained possible. Another assessment showed that different assumptions about altered minerals and pore-filling material could make non-liquid models more competitive. These alternatives do not prove that Mars's middle crust is dry. They show that the available measurements may not identify one unique pore material or saturation level. Liquid-bearing rock remains a serious explanation, but it shares the permitted space with other conditions that future evidence must separate. The global estimate, therefore, carries at least two layers of uncertainty. First, the exact local saturation and pore material remain debated. Second, the distribution of similar crust beyond Elysium Planitia has not been measured. A change in either layer alters the final inventory. The 1 to 2 kilometer equivalent remains a consequence of the broad representative scenario, not a confirmed planetary census. Several practical questions sit beyond the present evidence. Scientists do not know whether the water-filled spaces, if present, form connected pathways. They do not know the detailed chemistry throughout the layer, or whether similar conditions occur on the other side of Mars. The depth places the proposed water far beyond any direct sample obtained by the mission. Habitability is even farther down the chain. Liquid water could provide one requirement for a habitable setting, but InSight detected no organism or biosignature. The seismic result cannot establish energy sources, usable chemistry, stability, or life. The documentary can identify a potential environment for future investigation without turning that possibility into biological evidence. If the water conclusion remained alone, the tidal answer would still be important, but InSight's deeper signals showed that the possible reservoir is part of a much broader revision of Mars. The planet below the landing site is not well described as a series of smooth, uniform shells. The mantle and core results then change the context of that possibility. A heterogeneous planet cannot be assumed to repeat the same crustal structure everywhere. The evidence that makes Mars more interesting also warns against global uniformity. Different regions may preserve different histories, compositions, and pathways. The ocean-scale extrapolation is therefore best treated as a measure of what the local model could mean at maximum planetary reach, while the deeper discoveries show why that reach must be tested. High-frequency waves crossing the mantle were delayed and scattered in ways that support kilometer-scale differences in composition or physical properties. Some inferred domains may reach roughly 4 kilometers across. Their size pattern and the history of the planet support an origin in giant impacts near the beginning of Mars. These domains are not directly imaged boulders. They are regions inferred from how waves lost their clean shape. Mars's stagnant lid behavior may have mixed its mantle too slowly to erase them. If that interpretation is correct, the modern mantle still preserves differences created about 4.5 billion years ago. This mantle result carries a different confidence structure from the water estimate. The scattered signals are observed. The size and distribution of heterogeneities are inferred through models. Their connection with giant impacts is an interpretation supported by physical context. No planet-wide water extrapolation is needed to make the mantle complex, but the exact identity of every domain remains unknown. Deeper still, reflected and diffracted waves challenged the first estimate of the core. The earlier model placed a large, low-density metallic core beneath a compositionally uniform mantle. Later analyses found that a partly and fully molten silicate layer above the metal could explain slow, deep signals while moving the true core boundary inward. Two independent studies supported this layered structure. Instead of a metallic core extending to a radius near 1,830 kilometers, the revised models placed a smaller, denser core around 1,650 to 1,675 kilometers. Molten rock belonging to the mantle occupies part of the region previously counted as core. A later analysis added evidence for a possible solid inner core surrounded by liquid metal. The exact sizes and states remain open to revision, but the combined picture is no longer simple. A possible solid center, liquid metallic outer core, molten silicate above it, a heterogeneous solid mantle, and a fractured crust whose middle depths may contain liquid water. These are not 5 equally certain layers in a finished diagram. They are conclusions built from different events, paths, models, and assumptions. A responsible synthesis must keep their evidence grades visible. Ground motion is direct observation. Seismic velocities, scattering behavior, and deep boundaries are physical inferences constrained by that observation. Liquid-filled fractures are the preferred interpretation in the original mid-crust model. The extent of saturation and competing materials remain disputed. A 1 to 2 kilometer global water layer is a conditional extrapolation. A present habitat is a possibility, and present life is unsupported. Mantle heterogeneities and the molten basal layer are also inferred rather than photographed. Their ability to explain several related observations gives them scientific weight, while sparse seismic coverage leaves room for revision. The possible solid inner core is a newer result that future measurements must continue to test. This hierarchy does not weaken the answer. It reveals what makes the investigation valuable. A scientific discovery is not always a single object revealed at one moment. Sometimes it is a change in which internal worlds remain possible after measurements remove the simpler ones. Before InSight, Mars could still be described in broad terms as a cold crust above a mantle and core. After InSight, each region contained unexpected structure. The crust may hide liquid across an enormous volume. The mantle may preserve ancient collisions. The deepest mantle may still be molten in a chemically distinct layer. The core may be smaller, denser, and internally divided. The discoveries share one theme. Mars has not erased its past. Water that vanished from the surface may remain inside fractures. Material from early impacts may remain inside the mantle. Products of an ancient magma ocean may remain above the core. The apparently inactive planet has preserved changes that Earth-like recycling might have blended away. The direct answer can therefore be stated without the headline's ambiguity. NASA's InSight data revealed a local mid-crustal structure best explained in the original analysis by fractured rock containing liquid water. If that structure is common across Mars, it could hold an ocean-scale inventory equivalent to a global layer 1 to 2 kilometers deep. The global reservoir is not confirmed, and water saturation is not uniquely required. Beyond that primary answer, the same mission revealed kilometer-scale mantle heterogeneity, a probable molten silicate layer above a smaller core, and evidence for a more complex metallic center. Together, the findings replace the idea of a simple dead interior with a planet that remains layered, uneven, and scientifically unfinished. That is as far as the evidence can carry the title. The enormous water inventory is plausible and conditional. The mantle and core structures are powerful inferences with their own uncertainties. None was seen directly, yet all are constrained by vibrations that crossed a world no human instrument could enter. The investigation has moved from a dry plain to a possible ocean-scale reservoir, then through preserved impact domains, and down to molten rock surrounding the core. But its final meaning lies back where it began. A silent lander still rests on the surface, surrounded by a landscape that appears empty. The difference is that emptiness can no longer be mistaken for the whole planet. Insight remains where the investigation began, resting beneath Martian dust on a plain that offers no visible sign of what may lie below. Its solar panels no longer power new measurements. No mechanical movement announces another discovery. From a distance, the lander and the landscape around it appear equally still. But stillness is no longer the same as emptiness. For several years, the instrument listened as marsquakes and impacts sent energy through the planet. Those movements crossed layers that no camera could enter and no drill could reach. They returned to the surface, carrying small changes in time, strength, and shape. InSight recorded them once, but scientists can continue asking new questions of the archive. That archive has changed the meaning of the dry ground surrounding the lander. The surface remains cold and exposed. Its ancient channels remain empty. Yet the absence of visible water does not prove that every part of the old inventory left the planet. Some may survive as liquid inside deep fractures, although its amount, distribution, and even exact saturation remain unresolved. The same planet may preserve other parts of its past at greater depths. Irregular regions in the mantle may carry the material memory of collisions from the beginning of Martian history. Near the core, molten silicate may remain from an early separation of materials inside the young planet. The metallic center may itself contain more structure than the first models allowed. These findings do not make Mars secretly active in every familiar sense. They reveal something quieter. A planet can stop displaying much of its history at the surface while retaining that history within its interior. Water can enter rock. Impact debris can become part of a mantle. Heat and composition can preserve layers for billions of years after the events that formed them. One instrument, operating from one location, exposed this complexity. That achievement is also the source of the remaining uncertainty. InSight could listen only from Elysium Planitia. Its waves sampled particular paths rather than every region. Its measurements can constrain what is possible beneath Mars, but they cannot turn one site into a complete global survey. The next decisive answer will require new evidence. Other seismic stations could listen from different locations and compare the same events across several paths. Independent measurements could test whether the proposed middle crust continues far beyond the InSight region. Only then could scientists determine whether the possible water inventory surrounds much of Mars or belongs to a more limited geological setting. Until that evidence arrives, the uncertainty should remain visible. Mars may contain an ocean-scale amount of deep water, but the planet-wide estimate is conditional. The original liquid-bearing model is important, but other pore and mineral conditions remain possible. The lack of final certainty is not a space to fill with a more dramatic claim. It is part of the discovery left for another mission. There is a human lesson within that limit, although it does not need to become a claim about human importance. Exploration often begins by mistaking what can be seen for everything that exists. A dry surface looks like complete loss. A silent planet looks internally finished. A motionless lander looks as though its work has ended. Insight changed all three impressions without ever leaving its landing site. The dry world may still hold water. The quiet mantle may preserve ancient violence. The deep core may contain boundaries that remained hidden even after scientists first believed they had measured its edge. And the retired lander continues to produce knowledge because its old signals can be understood in new ways. The strongest result is therefore not a picture of a blue ocean beneath red stone. It is a more careful view of what evidence can reveal. Tiny movements at one point on the surface can place limits on structures thousands of kilometers away. Those limits can overturn simple models while still preserving uncertainty about the exact materials involved. The opening plane has not physically changed. Dust still surrounds the lander. The horizon remains bare, and the ancient rivers have not returned. What has changed is the meaning of that image. The desert is real, but it is only the outermost layer of the story. Beneath it may lie water that escaped the surface without escaping Mars, rock that remembers collisions older than any surviving landscape, and molten boundaries that preserve the planet's earliest heat. None can be seen from beside the lander. All have left some influence in the vibrations it recorded. The silence above Mars now feels different, because it marks not the absence of a story, but the boundary of our present shared knowledge. Mars did not reveal a hidden ocean waiting in darkness. It revealed how much of a world can remain hidden beneath what appears to be empty.